Imagine you're browsing real estate websites, and every property has a predicted price that's eerily accurate. Ever wondered how these platforms know what a house is worth before it even hits the market? Well, today we're pulling back the curtain and building our own house price prediction model from scratch using machine learning. And the best part? You don't need a PhD to do it. Just 30 minutes in Python. Why this project matters. Before we dive into code, let's talk about why this matters. The real estate industry moves billions of dollars every single day. Buyers want to know if they're getting a fair deal. Sellers want to maximize their profit. Banks need to assess property values for mortgages. And all of this relies on accurate price predictions. Machine learning has revolutionized this space, and linear regression is the foundational algorithm that makes it all possible. First things first, we need data. For this project, we're using the famous California housing dataset. It contains information about California districts including median income, house age, average rooms, population, and of course, median house prices. This dataset is perfect for learning because it's real, it's messy, and it teaches you how to handle actual data science challenges. Let's start by importing our essential libraries and loading the data. We'll use pandas for data manipulation, NumPy for numerical operations, and scikit-learn for our machine learning tools. This is the foundation of virtually every data science project. Python code importing essential data science libraries, including pandas for data manipulation, NumPy for numerical operations, and scikit-learn for machine learning. The code loads the California housing dataset using fetch_California_housing. Function stores features in X data frame with column names from housing.feature_names and target values in Y series named medhouseval. Finally prints first 5 rows using head and dataset dimensions using shape attribute showing total samples and features. Let's visualize what we're working with. The dataset has over 20,000 houses across California. Each row represents a district, and we have 8 features to work with. Notice how some features like median income strongly correlate with house prices, while others like latitude and longitude capture geographic factors. Understanding your data is crucial before building any model. Here's a critical concept in machine learning. We never train and test on the same data. That's like studying with the exact questions that'll be on the exam. It doesn't prove you actually learned anything. So we split our data into training and testing sets. The model learns from the training data, and we evaluate it on the testing data it has never seen before. The train-test split is simple but essential. We use scikit-learn's train_test_split function, typically using 80% for training and 20% for testing. The random_state parameter ensures reproducibility. Every time we run this code, we get the same split. Code demonstrates train-test split using scikit-learn's train_test_split function. X and Y are split into X_train, X_test, Y_train, Y_test with test_size equals 0.2, meaning 20% goes to testing and 80% to training. Random_state equals 42 ensures reproducible splits. Same random seed produces same split every time. The code then prints shapes using .shape attribute and lengths using len to verify split worked correctly, showing training set has approximately 16,512 samples and testing has 4,128 samples. Now for the exciting part, building our model. Linear regression is beautifully simple. It finds the best fit line through your data points. Think of it like this. If you plotted house size versus price on a graph, linear regression draws the line that gets as close as possible to all the points. But in our case, we're working with 8 dimensions, not just 2. So it's more like finding the best fit hyperplane through multidimensional space. Creating and training the model takes just 3 lines of code thanks to scikit-learn. We instantiate a linear regression object, call the fit method with our training data, and boom, the model learns the relationships. Under the hood, it's calculating coefficients that minimize prediction error using ordinary least squares. Code creates linear regression model by instantiating linear regression class from scikit-learn. The fit method trains model using X_train features and Y_train target values, calculating optimal coefficients through ordinary least squares. After training, Code iterates through feature names from x.columns and corresponding coefficients from model.coef_ using zip, printing each feature's coefficient formatted to 4 decimal places. Finally prints modeled intercept _, which represents the baseline value when all features are 0. These coefficients show how much each feature impacts house price predictions. What the model learned. Each coefficient tells a story. A positive coefficient means that feature increases house price. A negative coefficient means it decreases price. For example, median income has a large positive coefficient. As income in a district goes up, so do house prices. Ocean proximity might have a negative coefficient because houses further from the coast tend to be cheaper. The intercept is the baseline price when all features are 0. Now let's put our model to work. We use the predict method to generate predictions on our test set. Remember, the model has never seen this data before, so this is the real test of how well it learned. Code uses trained models predict method to generate predictions on x_test data, storing results in y_pred array. Creates comparison data frame using PD data frame with 3 columns. Actual containing first 10 true values from y_test using .values attribute. Predicted containing first 10 predictions from y_pred, and difference calculating error by subtracting predicted from actual. Then displays sample prediction by accessing first test sample using x_test.iloc 0 to show input features, multiplying predicted and actual prices by 100,000 to convert to dollars. Dataset stores prices in $100,000 units, and formatting with 0.2f for 2 decimal places. Look at these predictions. They're remarkably close to actual prices. Some are spot on, within a few $1,000s. Others have larger errors, but overall the model captures the general pricing patterns. This is the power of linear regression, finding mathematical relationships in complex data. Let's quantify how good our model really is. We use 2 key metrics. R² tells us the proportion of variance explained by the model. Closer to 1 is better. And RMSE, root mean squared error, tells us the average prediction error in dollars. Our model achieves an R² of around 0.60 and RMSE of about $68,000. That means we're explaining 60% of price variance, which is solid for a basic model. Computing evaluation metrics is straightforward with scikit-learn. R² score ranges from 0 to 1, where 1 means perfect predictions. RMSE is in the same units as your target variable, making it easy to interpret as average prediction error. Code imports evaluation metrics from sklearn.metrics, including mean_squared_error, R2_ score, and mean_absolute_ error. Calculates our superscript 2, R². Using our 2_ score, which compares y_test actual values against y_pred predictions, returning value between 0 and 1 where 1 is perfect. Computes RMSE by taking square root of mean_squared_ error, result using np.sqrt, giving error in same units as target. Calculates ME using mean_absolute_ error for average absolute difference. All dollar amounts multiplied by 100,000 to convert from dataset units. Final prints show model explains approximately 60.6% of variance and has average error around $68,700, providing clear interpretation of model performance. Not all features are created equal. Some have massive impact on price predictions, while others barely move the needle. Median income dominates. It's by far the strongest predictor. Location features like latitude and longitude also matter significantly. Surprisingly, house age has minimal impact in this dataset. Key insights. What we discovered. So what did we learn from this project? First, linear regression is incredibly powerful for its simplicity. With just a few lines of code, we built a model that predicts house prices with 60% accuracy. Second, feature selection matters enormously. Median income alone can predict a huge portion of price variation. Third, even a basic model provides actionable insights. Real estate agents could use this to quickly estimate property values and identify undervalued listings. Quote, "The best models aren't always the most complex. Sometimes a simple linear regression tells you everything you need to know, and understanding it deeply beats using a black box algorithm you can't explain." Andrew Ng, AI pioneer. Taking it further. Want to level up this project? Here's your roadmap. Start by adding more features through feature engineering. Create ratios like rooms per household or distance to city centers. Then try polynomial features to capture nonlinear relationships. Experiment with different algorithms like random forest or gradient boosting. Add cross-validation for more robust evaluation. Finally, deploy your model as a web app where users can input house features and get instant predictions. 60% accuracy with just 8 features. And there you have it. We built a machine learning model that predicts house prices from scratch in under 30 minutes. You learned how to load and explore data, train a linear regression model, make predictions, and evaluate performance. This is the foundation for more advanced projects. Next time, we'll tackle stock price prediction using time series analysis. If you found this helpful, smash that like button, subscribe for more hands-on projects, and drop a comment telling me what you want to build next. Until then, keep coding, keep learning, and I'll see you in the next project.